Alright, so a couple of announcements today. I'll be sending out notification about the Putnam exam. If you want to take the Putnam, strongly encourage you to do so, as well as the Green Chicken. These are many-hour math competitions. For doing that, you will be able to get homework exemptions for this class, because you'll be thinking deeply about math for quite a while. As promised, the itemized Cookie Monster has come to class, albeit a day late. I will send you pictures of Kayla and her Cookie Monster from her school. The colloquium today is on a strange probability problem with, hats being placed on people, and you're able to guess the color of your hat correctly, in some sense, more than 50% of the time, when your hat is equally likely to be black or white. And this has enormous applications to cryptography and economics. On Friday, at least 30 minutes of the class is going to be given to a former Williams graduate who's now at Goldman Sachs. He's going to come and talk about some of the financial math they use, as well as recruiting opportunities. There'll be a presentation on Thursday. If anybody's interested in having a lunch with him, please let me know and send me a CV if possible, and I will try to arrange for this. Again, I'm going to try to bring in people as I can throughout the semester, or at least provide you with contact people in industry as well as academia. So if you do want to pursue some of these things, use the Williams Network. That's one of the reasons why you're here and not just watching the Khan Academy at home. Speaking of which, you can now watch this at home. Okay, so I want to quickly review the stuff from chapters, I think it's 7 and 8, the probability density functions, cumulative distribution functions for real, valued random variables. This is going to be discrete, this is going to be continuous, they're going to be extremely similar. And so I think it makes a lot of sense to do them together. Sometimes people say probability mass function instead of probability density function, just like sometimes people write a sum rather than an integral. Eventually, as you go far enough in mathematics, you realize this is annoying, I have to use a different symbol depending on whether or not things are discrete or continuous. Let's just make the integral sign mean either an integration or a sum, depending on what kind of space I'm working on. And I think that's extremely good notation. So chapters 7 and 8. So we have a PDF, so the probability density function. And if it's discrete, we have things such as P of xi, and this is the probability my random variable x equals xi. And if it's continuous, I have P of x. In the discrete case, I have the sum of P of xi equals 1. Each P of xi is greater than or equal to 0. And in fact, in the discrete case, we can say something further. We can extend this a little bit to we know more than it's just greater than or equal to 0. We have an upper bound as well, right? It can't be larger than 1, because no event can happen with probability greater than 1. So we also have P of xi is less than or equal to 1. This is not the case in the continuous. In the continuous, we have the probability, say a less than or equal to x less than or equal to b, is the integral from a to b of f of x, I'm sorry, using p of x, p of x dx. And we would have p of x is greater than or equal to 0, and the integral from minus infinity to infinity of p of x dx equals 1. This is perfectly fine notation if you're only talking about one random variable, but if you have lots of different random variables going on, well, what random variable is p attached to? So frequently, we write p of x or f of x for the probability density function. And the advantage of that is we can then just quickly look down, and if we quickly look down, we can then see, this is the density associated to the random variable x. Now, a big question later in today is going to be, well, what happens if we combine a bunch of random variables? Is there a nice way to get the density function for sums of random variables, or products of random variables? And unfortunately, in general, it's going to depend on what the random variables are. So let's do an extreme case. So for an extreme case, I want to look at x plus y. Can somebody think of some extreme cases for y that would make this very interesting? What would be a good choice for y, or a bad choice for y? So one case would be, case 1, y equals x. What would be another extreme case?
Negative x.
Y equals negative x. So in these cases, I'm going to have very different behavior for x plus y. In this case, x plus y is pretty easy. X plus y is identically 0. Right? Doesn't matter what the distribution of x and y are. In this case, x plus y is just twice x. And as a nice case, I could say, let's let f of x be 1 if minus a half less than equal to x less than equal to 1/2 and 0 otherwise. And same for f of y. So it'll be 1 if minus a half less than equal to y less than equal to 1/2, 0 otherwise. So what's nice about this is x and y have the same distribution. And in fact, x and negative x have the same distribution. So if I want to try to understand x plus y, it's not enough to know just the probability density functions. This is very similar when we were trying to get the formula for conditional probabilities. When we tried to get the formula for conditional probabilities, we're like, well, okay, if I know the probability of A and the probability of B, can I somehow figure out the probability of A given B? And we saw there's no way that can happen. So similarly over here, just knowing the density functions of x and y can't be sufficient to understand the density function of x plus y. So we're going to need a lot more information. So there's two different routes to go. One route is to give you what's called the joint density function, where I tell you what's the probability I get a pair x comma y. Well, if I know the probability of getting a pair x comma y, it makes sense that I should then be able to figure out things like x plus y. The other possibility is to assume x and y are independent. So knowledge of x has nothing to do with knowledge of y. And in that case, we actually get beautiful formulas for the density of x plus y. Alright, so if we look at the two cases, the continuous and the discrete, which would you rather look at in terms of a random variable? A continuous random variable or a discrete random variable? Discrete. Okay, good. So we've got both sides. Why discrete?
Because you can count the number of events that are happening.
So you can just basically count how many events. This is really maybe a good way to enumerate the possibilities. So discrete definitely has some good things for it. Continuous.
You can just integrate it. If it's an integrable function.
If it's an integrable function, you can integrate it. So on Friday, did we talk about the fundamental theorem of calculus and signed areas under curves? Did we state the fundamental theorem of calculus here? Okay. I think I actually stated the fundamental theorem of calculus in complex analysis. And so the two classes are almost at the same place for very different reasons. Okay. There are not that many fundamental theorems you have heard of. Okay. You may have heard of the fundamental theorem of linear algebra. I think it's a little bit pretentious to call it fundamental theorem. Fundamental theorem of arithmetic, fundamental theorem of algebra, these ones I like. Can someone tell me the fundamental theorem of calculus? Fundamental theorem of calculus.
The area under a curve is equal to the antiderivative
Okay.
As
The antiderivative.
x equals
The big F prime is the left. This is an example of good notation. Right? I need a notation for the antiderivative, for the integral of little f. Let's use big F. Somehow it's been made bigger. And you can see that the symbol is now related. The important word here is area. This is often forgotten. People often say the fundamental theorem of calculus is the following. The integral from a to b of f of x dx is big F of b minus big F of a with big F prime equals little f. if you don't say area, I would say this is the fundamental definition of calculus, right? You have to say, what does this thing on the left mean? If the thing on the left means take the antiderivative of little f and evaluate it at b and subtract at a, yeah, this is going to be true. It's also not going to be impressive or useful. The content of the fundamental theme of calculus is that this is an area. And so for us, areas will be related to probabilities. And that's why we care so much about all of this, is this allows us to calculate probabilities of events. So if I give you, a nice function that integrates to 1, here's a, here's b, then the area under the curve from a to b of, say, f of x dx will be the probability that x is between a and b. So now we actually see an application of integration. Why do we care about integration? It gives us areas under curves. These areas under curves will be the probabilities that events happen. Now, there are 4 possibilities. I have a less than equal to x, less than equal to b. Instead of less than or equal to, I could have used less than. So I have 4 possibilities, both less than or equal to, 1 less than or equal to, or both less than. They differ by whether or not I include the endpoint. In a continuous random variable, what's the probability that I'm exactly equal to a? 0. I'm basically integrating from a to a of f of x dx. So for continuous random variable, the probability of singletons are 0. What about for discrete events? Are the probabilities of singletons always 0? No, otherwise the theory of discrete random variables would be, not even worth studying. Things have to happen, right? So for discrete, it's extremely difficult, and unfortunately, this makes a lot of discrete systems significantly harder to analyze. The question is whether or not you end up just on a boundary. Well, if it's a continuous random variable, I don't really care, do I include the boundary or not? It's not going to affect the probabilities. But for discrete, did I make it in exactly 6 shots? Well, yes, if I include or don't include exactly 6, that will make a big difference.
Are we assuming that the area, the total area of the graph is 1?
Yes. So for a continuous random variable, the area under the graph is 1. And so if that's not the case, then it's not a continuous random variable with a continuous random variable's probability distribution.
It's been frequently said in this and other classes that, professors really have to try to create integrable functions.
Yes.
I'm
willing to do the work for you. I'm willing to do it.
No, even though the discrete functions are slower and more painful,
right?
Are they able to process more functions that integration can't?
No, because the problem is if you do something that's discrete, now you need a good theory of discrete summation. Okay. And we don't really have good formulas for sums of discrete random variables. I'm going to show you a beautiful technique to use differentiation to actually evaluate sums of discrete random variables. And you might think that this is a little bit strange to be differentiating, sums, but it allows us to evaluate some sums very well. So, based on the question you just asked, Chris, let's change the order of the topic today a little bit, and let's consider the following example. So let's let fx of x equal 2 plus 3x minus 5x squared, 0 less than equal to x, less than equal to 1, 0 otherwise. So in the book, I go on at great lengths that this is a cookbook example that nobody cares about. Okay? I do not know any problem in the world where this is the underlying density function. Okay? Why then am I going to spend a couple of minutes talking about this? I'm sorry? Okay, so one thing is it's actually, it's a nice cookbook example, so things will work out. But why do I want to spend so much time on something that has no direct real-world application? Other than I've got to fill up 50 minutes somehow, right?
To demonstrate later.
To demonstrate, right? The whole point of a cookbook example like this is to talk about the techniques with easy numbers. I want to work with an easy function where I can do the integration quickly. How many of you remember integration by parts? If you don't, just raise your hand and just promise me that you will learn it very quickly. How many of you remember U substitution? Again, raise your hands and promise me you will learn it. Trig substitution. That's less important. Okay? Partial fractions.
While integrating?
Yeah. Oh yeah.
Awesome.
Partial fractions are not just because we're sadistic professors and we can make you do these things. Partial fractions are quite useful, especially for differential equations, especially for complex analysis. Partial fractions are very useful. For the most part, I'm going to stick to use substitution and integration by parts for the examples. But obviously, the more functions you can integrate, the richer the set of examples we can look at. So let's look at this function. Is the function non-negative? So some values of x, it should be very easy to check that it's non-negative. Which values of x are easy?
1 and 0.
I'm sorry?
1 and 0.
1 and 0. But now, of course, this is otherwise. So anything greater than 1, it's clearly fine. Anything less than 0, it's okay. The difficulty is what's going on between 0 and 1. So we have several ways to show it's non-negative. Show fx of x is greater than or equal to 0. Method 1, 2 plus 3x minus 5x squared, if we factor it, so we've got a 5, so we want a 5 and a 1. I think I want a 2 and a 1. I think this works. I get 2 plus 3x minus 5. Okay? So, if you don't remember how to factor like this, what could you have done? Quadratic formula, right? So you could always find the roots with the quadratic formula. If you happen to notice this, it's very easy to see it's non-negative in the region. This factor is never negative between 0 and 1. This factor is is never negative between 0 and 1. So you're done. Another way you could show that it's greater than or equal to 0 is to note for 0 less than or equal to x less than or equal to 1, we have x squared is less than or equal to x. So 2 plus 3x minus 5x squared is greater than or equal to 2 plus 3x minus 5x. And that's going to just be 2 minus 2x, or 2 times 1 minus x, which is, again, greater than or equal to 0. If you didn't remember that, you could plot the function. This is a parabola. You could find where's the vertex of the parabola, where does the parabola hit the x and the y-axis. You know, one of the places it hits is x equals 1, the other place it hits is in a negative place. So the third way is to plot. Okay? So, you know, you have to do some type of algebra to figure out that this function is non-negative. Alright? Does this prove that this is a probability density?
No.
No. What do we need to check? Right, so does the area under the curve equal 1? What do you think?
Probably, seeing as you picked it as an example.
So one thing is probably seeing I picked it as an example, but maybe I deliberately chose it as an example because it doesn't work. Well, one thing is if I look over here, I know it's greater than or equal to 2 times 1 minus x. If I integrate this, I'll get 1 minus x squared over 2. And then when I plug in x equals 0 and 1, what would I get? I think I get 1 if I plug in 0 and 1. So just looking at this inequality here, I'm quite suspicious that it's going to integrate to 1. Because I think if I integrate this, I get 1. And since this is not going to be an equality most of the time, it's going to be an inequality most of the time, the area should be larger. So without even doing the integration, I have reason to believe that it's not going to integrate to 1. Also, as the person who wrote the problem, and I deliberately wanted something that doesn't integrate to 1, I also have another reason to believe that the integration will not come out to be 1. Because I want to show you that if something has to go wrong, this is what you want to go wrong. So, people will sometimes ask me, which of my kids do I love the most? Now that they're both doing a good job sleeping, for the most part it's a tie. And that's not a question I will answer. If I had to ask you, which property would you like to fail for a function that you want to be a probability density? The fact that it's non-negative everywhere, or the fact that it integrates to 1? Integrating to 1 is a much better property to fail. We can fix that. All we have to do is just rescale the function. And so it's not going to be hard to convert this to a probability density. If it was positive in some places and negative in others, then we're out of luck. We can't fundamentally rescale it. So let's do the calculation. Show it integrates to 1 if it is a probability density. Alright, so now we need to integrate from 0 to 1 of 2 plus 3x minus 5x squared. And so if we integrate this, we get 2x at 0 and 1 plus 3x squared over 2 at 0 and 1 minus 5x cubed over 3 at 0 and 1. Have I made any calculus mistakes? Okay, so if we put in x equals 1, we get 2 plus 3 halves minus 5/3. Common denominator is 6, right? So we get 12 plus 6 minus 5 over 6. Minus 10, I was going to say minus 10. Alright, and so...
it's 9.
No, I was going to say, and this is going to be 9
Plus
over
9.
here. So there's the algebra mistakes. There we go. Okay. 12 plus 9 minus 10 over 6, which is 11/6, if I've done it correctly.
Yeah.
So it does not integrate to 1. It's not a probability density. But it's very easy to make this a probability density. So all we have to do is let's let g of x be 6/11ths of f of x. And that is a density. There's a lot of subjects where you really don't thrive until you have years of experience. And sometimes it's hard when you look at something to see how important is this. This is one of the most important observations in the course. This seems quite trivial. If it doesn't integrate to 1, we'll just rescale it. There's a lot of times I know something is a probability density, and I have some very painful integrals to do. And I can often break up the integrals into, maybe I'm integrating over a sphere in 2014 dimensional space, which you will do at some point. Well, no, I'm not going to make you integrate over a 2014 dimensional sphere. I'll make you integrate over an n-dimensional sphere where n is arbitrary. So technically, you've all taken Calc 3, you're all supposed to know change of variable formulas, you're supposed to have seen spherical coordinates, maybe not in n-dimensional space, but Wikipedia and other sources exist. You can find the parametrization for the n-dimensional sphere. It turns out, for a lot of the problems, you can split off the angular dependence in one direction and the radial dependence in another, and have two types of integrals. And a lot of times you have things that don't depend on the angles. You have things that only depend on how far are they from the origin. And you can do the radial integration. And then whatever hell is going on with the angular integration, it has to be such that it gives you a probability distribution when you do all the integration. So it'll be the normalization constant that you need. And so this idea of rescaling can frequently be used to eliminate the need of doing very painful calculations. And so, right now it doesn't really look like this is, that impressive of a fact, but it's going to be absolutely useful in saving you enormous amounts of time. Now again, if you want to do spherical integration in n dimensions, by all means feel free to do so. You'd have to figure out what the parameterizations are. You would have to then figure out some kind of induction to use because n is arbitrary and not fixed. This will save you a lot of time. So it's worth isolating this as a principle. The renormalization principle. If f is non-negative and has a finite integral, then g of x equals f of x over the integral from minus infinity to infinity of f of x dx is a probability density. Alright, so why did I put on the condition that the integral is finite? So why did I add that condition?
Because you don't want to divide by infinity?
Yeah, I don't want to divide by infinity, because if I divide by infinity, then I'm getting something that's identically zero. Right? So if I'm going to be able to normalize things, you know, I can be off by a factor of 2, I can be off by a factor of 5. If I'm off by a factor of infinity, I'm really off. Right? I can't fix a mistake of that magnitude. Okay? I can fix a mistake on the order of 2, on the order of 3, on the order of 5. That I can do. Okay? As a nice way of going from here, how many of you have seen uncountable sets? Alright, so enough of you have seen uncountable sets that I want to just do an example to show that we can't assign a discrete probability to an uncountable set of events. I'm going to show that this can't be done. Okay? If you haven't seen uncountable sets before, don't worry about it. So, uncountable sets. Say have a sequence x alpha, and it's uncountable. We cannot assign probabilities unless at most countably many as 0. And in that case, we're kind of cheating. If I give you an uncountable set, I want to assign non-zero probabilities to every element of the uncountable set. Right? And I say, yes, I can do that so long as I assign the probability of 0 almost all the time. Okay. So here's the proof. Let S0 equal the set of all x alpha such that the probability of x alpha, well, I'll do the joint case. Sn will be the set of all x alpha such that the probability of x alpha...
Wait, for that, is it at most countably linear or non-zero?
Oh yes, a non-zero, yes, thank you. A non-zero. So Sn is going to be the set of all x alpha such that the probability is between, what else is in 1 over n plus 1, 1 over n. And I will not include the left endpoint, but I will include the right endpoint. Okay? So I claim each x alpha is in exactly 1 Sn. And goes from 1 to infinity. Right. I've assigned some probability to x alpha. The first one, x1, is everything that's greater than a half and less than or equal to 1. S2 is everything that's greater than a third and less than a half. So this is a partition. Right? So does everybody agree that each x alpha is in 1 and only 1 Sn? Could each Sn have only finitely many elements? So this is where you need to know a little bit about countable and uncountable. Yes?
No, because if there are countably many countable sets, then
Right.
the overall thing would be countable.
So if each Sn has We can even do it better than this. If each SN has finitely many elements, cannot get uncountably many. So one of our sets, Sn, has to have infinitely many elements. Which set has infinitely many elements? So one has infinitely many elements, say Sm. But now I have a set with infinitely many elements, and everything in it has probability at least 1 over m plus 1. How much probability have I given out?
Infinity.
I've given out infinity from.
Infinite.
Given out, at least infinity times 1 over m plus 1 probability, which is greater than 1. Okay? I was far too generous. Okay? I cannot give out that much probability. Remember, certain operations with infinity are defined, certain operations with infinity are not defined. I can multiply infinity by any non-zero number. That's okay. I cannot multiply infinity by 0. How many of you are really comfortable with dangers of multiplying infinity? Alright. I will give you, I think, my most enjoyable example of the dangers of multiplying by infinity. What's infinity times 0?
0.
No!
That would be too simple, wouldn't it?
Yes. Infinity times 0 is actually negative 1. Alright? I will prove that infinity times 0 is negative 1. I think I might have done this in 105. We'll see if it seems familiar. So draw a circle. Right? Here's the x-axis. Here's the y-axis. Here's some line with slope m. And now I'm going to draw the line perpendicular to this. So you have to remember, your old algebra. So does anybody remember what the slope of this line is? Negative 1 over m. So it's a nice exercise to prove that if you draw a line perpendicular to another line, the product of their slopes is negative 1. So the product of these two slopes is negative 1. I get negative 1, negative 1, negative 1, negative 1, negative 1. Now I align with the x and the y-axis. What's the slope of the y-axis? Infinity. What's the slope of the x-axis? So I get negative 1, negative 1, negative 1, negative 1, undefined, negative 1, negative 1, negative 1, negative 1. In this problem, what is infinity times 0? Negative 1. In this problem, infinity times 0 is negative 1. You've got to be extremely careful. Okay? There's a very natural interpretation here for what infinity times 0 should be. So, consider the following limits. The limit as x goes to 0 of x over x squared, the limit as x goes to 0 of x squared over x, and the limit as x goes to 0 of x over 1701x. Okay, in all of these cases, I have 0 over 0. In this case, what do I get? One over x, and so as x goes to 0,
Plus or minus infinity.
plus or minus infinity, I can put in x goes to 0 through the positives, so I'll get infinity. In the second case, I have x squared over x. This is going to be the limit as x goes to 0 from above of x. That's going to just be 0. And in this case, it's 1 over 1701. As a nice exercise, try to prove similar things for infinity minus infinity, or infinity times 0. These operations are not defined. It's not enough to just know you have infinity over infinity. You need to know how rapidly are the infinities changing. Okay? So you've got to be extremely careful about stuff like this. Unless you want to move into like economics or physics, and then you can, But the good ones in those subjects are actually very good about dealing with infinities. And so,
Like integrals of delta functions.
like integrals of delta functions, or Feynman path integrals, where you have all these, absolutely amazing. Okay, but you should be aware of the issues. And what do we need to make the subject rigorous and technically sound? We've got to be very careful about stuff like this. If my function integrates to plus infinity, it's not going to be a probability density function. I need something that has a finite integral. Okay, we talked on Friday, I think, about CDFs, cumulative distribution functions, calculating the probability of an event at most x. And so what I'm going to do is I'm going to hold off on doing a little bit more of CDFs for now and just do some examples. So, again, it's always a question of which cultural examples do you want to choose. I will try to resist the temptation to take sports examples. I will hope that everybody has at least played some game in their life with die, and you've rolled a 6-sided die. If not, the die looks something like this. One. I don't actually remember now. I know opposite 1 is 6. I don't know, well, so I can probably put 2 over here. But then in orientation, I don't remember what comes over here. How the die is oriented. We'll just assume, this is probably like Wikipedia to the rescue, but we'll assume it's something like this. So I have the numbers 1, 2, 3, 4, 5, 6. If the die is fair, each of these numbers is equally likely. And what you will frequently do is, if you're playing a game like backgammon, you'll roll 2 die at the same time. And sometimes you only care about the sum, sometimes you care about the individual values. Let's assume we only care about the sum. What number do you think is the most likely number to be rolled? What numbers do you think are the least likely?
7 is most likely.
7 is most likely, least likely? 2 and 12. So we roll 2 fair die. x1 is the value of the first roll. x2, value of the second. x3 is the sum. Now if I look at x1, what are the possible values for x1? What are the probabilities? So what are the possible values if I just roll 1 die, if I only look at the first die? 1 through 6 and? All evenly distributed. So the probabilities are 1/6 if x is in 1 to 6 and 0 otherwise. It is more complicated if I look at 2. So for 2 dies, so x is x1 plus x2. The possible values are 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many ways can I roll a sum of 2? 1. I have to roll a 1 and a 1, and so the probability would be 1 out of 36, because there's 36 ways to roll 2 die. What about rolling a 3? 2 ways. 1, 2, 2, 1. And so it would be 2 out of 36. Rolling a 4. 1, 3, 2, 2, 3, 1. 3 out of 36. The pattern is hopefully becoming clear. 5 would be 1, 4, 2, 3, 3, 2, 4, 1. 6 would be 1, 5, 2, 4, 3, 3, 4, 2, 5, 1. And that'd be 5 out of 36. And I'll do one more. 1, 6, 2, 5. That's painful, but there is a reason I want to write this. 3, 4, 4, 3, 5, 2, 6, 1, 6, 1, 3. And now things go down. What's nice here is you can see a triangular shape. And the sum of 2 rolls of a die is actually going to be like a triangular function. one of the big questions we'll be trying to study later in the semester is, well, what happens if I roll 30 die? What happens if I roll 50 die? What happens if I roll n die? What can you say about the shape? It turns out it's a lot easier to analyze the sum of 4 die than the sum of 3 die. And the reason is if I roll 4 die, x1 plus x2 plus x3 plus x4, I can group it like this. And I know I have a triangle function here, I know I have a triangle function here. I'm basically adding something to itself. It's not that much worse to do sums of 3, but this trick of grouping parentheses is very nice. So in the book I actually write down, using absolute values, what the formula is for each of these. You can write it down in closed form expression. The real interest is what happens when you roll n die as n gets very, very large. You think of some kind of random process with all these things going on, and you want to understand the general overall behavior. So the goal, and hopefully we'll start that on Wednesday, is to study x1 plus xn as n goes to infinity. We want to understand the limiting behavior of many rolls. One of my guiding principles is I would much rather do a lot of easy problems than one really hard problem. Okay? Is the quadratic formula hard? No. Is it pleasant? Do you enjoy doing it? No. But you can do it. Right? If I can reduce something to a bunch of quadratic formula problems, that's fine. It's mechanical. I can just work through it. What I want to do is when I study all of these rolls, is I want to understand the behavior of n rolls by just understanding the behavior of one roll and somehow understanding how things combine. In order to understand this, what do you think we're going to really need? We can do a great job if we have what? What do you think we need to get a good understanding of this sum? What do you want to assume about these random variables x1 through xn? What do you want to assume about these rolls of the die? That they are
mutually distinct. They're not going to influence each other.
Okay, so what's the word for that?
Mutually distinct.
Not mutually distinct. That they're independent. Right? Independence is going to be key if have independence. We'll see a lot of formulas are significantly easier if we have independence. What's absolutely fascinating is the two most important quantities associated to a random variable are its mean, or its average value, and its variance, or how spread out it is. And it turns out, if you have a bunch of different random variables, the mean of the sum is the sum of the means. That's nice. You have this linearity. It's not the case for variances. And in fact, if you think about our example from before with x plus x and x minus x, it's not surprising that I have absolutely no idea what's going on with the variance. And there are a huge number of problems that can be solved by just understanding linearity, where we lose independence. In the real world, how often do you think you have independence?
Not too frequently.
Not too frequently, right? For the most part, things impact each other. And so as you change one thing, that's going to affect lots of other things at the same time. It's going to make the analysis extremely complicated. All right, so the last thing I wanted to do today was talking about tossing coins. So this is the last of the standard examples which we're supposed to be doing. So toss n coins, all fair, all tosses are independent. So if I toss n coins, let's let x be the number of heads in n tosses, and let's let xi be the number of heads in the ith toss. So x is the sum I goes from 1 to n of xi. Can somebody give me the probability function for xi? What are the possible values here? So I toss one coin. What are the possible values for the number of heads?
1, 1, 1 or 0.
I'm sorry?
1 or 0.
1 or 0. And what are the probabilities of those events going to be? 50-50. Right. So in order to save time for later, I'm going to write it, it's 1 with probability 1/2, 0 with probability 1/2, and anything else has probability 0. If I were to replace the coin with probability p of heads, how would this change? This would now be probability p, this would be probability 1 minus p. So it's not that hard. I can try to understand the sum of n tosses by understanding what's going on with just one toss, if the tosses are independent. I can also try to understand it directly. So now, let's look at the density function for here. And sometimes, instead of writing little x, we might choose to write a different letter. We might choose to write k. Why would we write k rather than x? Does it matter? Does it matter if I use k or x for my variable?
Isn't k usually used for integer?
K is usually used for integers. So if I write k, I'm trying to give you a clue. Hey, think integers. You're not going to get root tooth of a head. Right? So we often use something like k to just give us a little clue as to what we're studying. Could I use a smiley face? I could. Right? Yeah, I would be laughed at by the mathematics community, but I could use a smiley face if I want.
You need to make it prove something really phenomenal with this smiley face.
Right, I could do something like maybe Prince, who had that beautiful symbol for his name at one point. Maybe he could get away with that. What's the probability I have exactly k heads? Well, can you tell me what are the possible values for k? What's the smallest value for k? What's the largest value for k? Good, 0 less equal to k less equal to n. And then the probability will be 0 otherwise. Now, if I want to get k heads and n tosses, how many ways are there to choose which coins toss to a head? And choose k. And then for each of those tosses, what's the probability I get a head? 1/2, and I have k heads. And for the tails, what's the probability I get a tail? I want to write 1/2 in a different way. 1 minus 1/2. Right? The probability of a tail is 1 minus half. Yes, it's 1/2. But this is a much better way to write it. How many tails do I have to have? N minus k. And so this would be the probability of getting exactly k heads when we toss the coin n times and it's fair. If the coin were biased and had probability p of heads, all that I would do is I would change this to p and to 1 minus p. And if you think about it, all the strings that have exactly k heads have the same probability. Each head happens with probability 1/2. Each tail happens with probability 1 minus 1/2. So I actually can write down in closed form the probability density function for tossing a fair coin n times, or tossing n fair coins simultaneously. Turns out those processes are the same. We will see later why we would actually care to calculate probabilities like this. But these are good things to do. Okay, so now on the next lecture is going to be, I think, chapter 9 on expectation. So we're going to see analogs of Taylor series and probability, and we're going to get into the linearity of expectation eventually, which is one of my absolute favorite topics. The number of problems we can solve, including how you should find your spouse, or how your boss is going to hire you, are amazingly solved using this.